sir.
Yeah.
Sir, what about the reference material of this subject?
Mainly the reference material, mainly there are books for this BEEE. There are many books available from the different publishers. All the books are available in the library over here. But I'll look into the which are the one I can get a soft copy of, and I will share that soft copy in form of material. Like there are no other material. Like there are basic PPTs, and then there are some examples that you have to do. So other than there is no extra material that you might be needing, but definitely I'll share some books for this subject. Get some books for in the form of soft copy, so you can read it at your home. Okay, so now let's begin. Let me share my screen. Okay, so initially when we started this chapter, we had started with first KCL, and we know that KCL state that if you have a node at in your circuit, all the currents coming in and going out, the algebraic sum between that two, keeping the sign, like if there is incoming current, if I consider this a positive, outgoing considered as a negative, in that case the algebraic sum between all the currents would always be 0. And there is one more rule, that is KVL. According to KVL, travel loop, summation of all the potentials. For an example, voltage source over here, a passive element here. This is a resistor. It will basically draw a current, and due to that, there will be a voltage difference across this resistor as well as this resistor. So if I do an algebraic sum between this three, then again that would be 0. And you have to keep in mind the sign. If you are going from negative to positive with the voltage source, then we will consider it as a positive. Okay, so if I travel like this, negative to positive, and if it's a voltage source, then it would be considered as a positive sign. And if I'm going from positive to negative, okay, positive to negative in the direction of my current. See, this is the direction of current. And if I'm going traveling in the direction of current, then I'll consider this as a drop, and I'll consider it minus. So minus IR1. Okay, so these are the basics of KCL and KVL. Now, based on this KCL and KVL, we are going to have two different analysis, a mesh analysis and a nodal analysis to solve the various problems. But before we start that, let's go ahead with the series parallel. Then we have covered series parallel in that same lecture, and in series parallel we have derived two equations. Basically, that's how you find out the equivalent resistance R. In case of series, it would be R1 plus R2 plus R3. If there are three resistors in series, if that connection is in parallel, in that case your equivalent resistor is 1 upon R equivalent. Keep this in mind. It would be always in 1 upon R equivalent. So like if you find this term, that is not actually your R equivalent. It's actually inverse of this term. So 1 upon R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3. So always there is a saying, like always in series, if there is a resistor will increase if it is in series, be it a very small increment, but always the resistor will increase. And in case of parallel, the resistor will decrease due to the parallel connection. Let us say this is a 100 ohm resistor. If I add a 10 ohm resistor over here, what would be my overall new resistance? It will be always less than 100, and it will be less than 100, not by 10, like, but it will be always less than 100. Okay, due to this factor, it is like always 1 upon R1, 1 upon R2. So it would be basically 1 by 10, 1 by 100. It would be point 0.1 and 0.01, so 0.11, and again you have to go inverse. So 1 by 0.11 is the answer. Okay, let's see what is the answer. So it is basically 1 by 0.11, I can say. and it is actually 9 ohm. So it is always less than the two resistance in the parallel. But in case of series, it is always greater than the individual resistor. Can be a small question in Viva. Okay, then we have not covered this part. I will come here later on. It is already written here, see, to be defined in a later chapter, like how you calculate a capacitor inductor in series and parallel, but it would be considered later on. Okay, then we have seen this example, how to solve this series example problem. Okay, how to find out how to solve it little by little. Okay, first I'll solve this, then I'll solve this, then I'll combine that in series, and then again with this one parallel. How can I solve this? That's the way. Then we have gone through, and there was one, like what if there are three resistors instead of two? There was one question raised during the last lecture, and I have told you that we'll see how this equation came. So basically whenever you consider this circuit, we always know V is equal to V1 plus V2. Okay, and from this equation we can get this equation. Okay, how we'll get this equation? So I know V1 is equal to I into R. Okay, this is my current flowing through this circuit, so I can say V1 is equal to I into R1. Now what is the value of I? What would be the value of I? So we can say from this overall circuit, if I consider this to be in series and I placed it as like R equivalent, or I can say R1 plus R2, in that case my R would be V is equal to IR. So my I would be V by R equivalent, and that is nothing but V by R1 plus R2. Now I'll put this I over here. So V1 is equal to basically V1 upon R1 plus R2 into R1, this R1. Okay. So this is how this equation works. Now let's add a one more R3 over here and see what will happen this time. So again, what would be my current I? I is equal to V upon R eq. Now I R eq, equivalent resistance of this three. This is a series connection. So obviously it would be R1 plus R2 plus R3. Okay, that was V. So V upon R1 plus R2 plus R3. Now again, what is V1? So V1 is still same I into R1. There would be no change here. Okay, there would be no change here. It would be V1 is equal to I1. I into R1. So if I substitute I can say R1 plus R2 plus R3 into R1. So it is same like this if there are 3 resistors or 4 resistors, but just difference is this part. Here you have to consider total resistance. Okay, but it must be in series. There, if there is a parallel connection in between, you cannot like do a total. But if it is in series connection, you can get a total, and a voltage division rule will work in all the case. Same way, the current division rule will work as well. But here you can do a same analysis over here, and you will get the same equation. But here also, if there are more than this, you can go ahead with more currents. Like you can find out a current in 3 branches or 4 branches. It is possible with that as well. So this rule by the case have more. Now we'll move ahead, and yesterday Ankur sir has taken this part, star delta transformation. Here the first thing is that we are not going into derivation of the star delta transformation, but we'll directly do using equation. We'll convert the star into delta and delta into star. Okay. So first, what is the star connection and what is the delta connection? So whenever you see 3 resistors are connected between 3 points. See, let us say I can say this is the 3 point. This is my first point, my second point, and this is my third point. And if I can connect 3 different resistors in between this 3 point, In that case, either I am connecting it in star or delta. Okay, first let us take star. So what will happen in star? I'll connect all three resistance with one common connection. This is my common connection between all these three resistors. This is a common connection. Let us say this is RA, this is RB, and this is RC. So the one end of each resistor, RA, RB, and RC. See, this is the one end of each resistor is connected at a common junction, and this is a star formulation. You can see it looks like a star. You might see it like this sometime. You might see it like this sometime, but this is also a star. If a resistor is like this is also a star. The basic of the star is still there. There are three nodes, three resistance RA, RB, and RC, and all these three have one common connection at this point. So this is again a star. What is delta then? Delta is one in which there would be no common connection between all these three resistors. So there is only a one way to connect it like that, and that is this. And the third one being like this. So now how to name this? If this is A, this is B, and this is C, I'll name this resistor as RAB. Resistance between point A and point B is known as RAB. This would be known as RBC, and this would be known as RCA. Okay, you can write like AC as well, but always try to write CA, so it would be have like whenever you write equation, it would be helpful. Always going in one direction. So I'll write CA rather than AC. Okay, it's the same thing. I can write RBA as well, but I will travel either like this or this, and I'll name it like that. Okay, if I name this as AC, then I will name this as CB and this as a BA. I'll alter all three names. Okay, so this is how you can find a star or a delta. You can identify a star or a delta using this unique feature. Okay, there is a one common connection in case of star, and there is no common connection in case of delta. You can see always a two resistor will be connected at one point, but there would be no connection where are connected. See here, no connection. This is a star and this is a delta. And at many places you will see you have to convert from this to this or this to this. So how to convert that? That is basically star delta transform, and how to do that. So to convert a star to delta, we have one basic equation, and that equation is this. See, first of all, whenever you draw a delta from a star, see, I am converting this star to delta. Here the node A, B, and C would be as it is. The common resistance would appear over here, and that would be named as RAB. A common resistance would appear over here, that would be named as RBC, and my third branch of delta would be like this, and that would be RAC. Now to find out RAB, I'll take help of RAB, RA, RB, and RC. But how? Whenever you're finding RAB, a delta resistor from a star, this is a star, I am converting it to delta. So in delta you will see a two combined nodes A and B. So what would be the equation? I have to add this two first. So which branch I am finding, I'll add that to. So I am finding for RAB, so I'll add RA, I will add RB. Other than that, also there will be influence of this. If we go in a proof, we can see that this equation is basically hang up proof over there, but we are not going into that. But the third parameter here would be multiplication of first two resistors RA/RB and division by resistor C. Same way we can write for BC, so it would be RB plus RC plus RB RC divided by RA. Okay, simple. whichever branch is remaining would be coming in denominator in case of your star to delta transformation. For delta to star, for reverse transformation like this, there is a with RA, RB and RC. I'm going from this to RAB, RBC and RCA. So star to delta will be having this equation. RAB is equal to RA plus RB. Okay. AB, multiplication of AB, division by C. I'll add all these three. And same for the other two branches. In case of reverse connection, delta to star, again, see, whenever you draw a star from the delta, so I'll be having a 3 resistor with a common point. See, I'm drawing a delta over here, so you can better understand it. So here, this is RAB and this is RCA. So in between that two, there is the resistor, whatever coming in between this two would be always RA appearing between BC and AB. So B is common here. See, B is common here, B is common here. So this is my RB and this is my RC. Keep that notation in mind. Just I cannot say this is my RA. Otherwise, what will happen? I'll write the equation in accordance with RA, but actually I should be writing it with RB. So you cannot randomly name it. Okay, whichever resistor is between that two other branch, depending on that, I'll decide the name. This is RA. Why? Because it is in between RCA and RAB. Or you can directly name it with node itself. Okay. Yes, you can see this is node A, so I can say this is RA. Okay. Now, what is the equation? To find out this RA, I'll be dependent on this two branch and there will be effect of this third branch. Okay, so whatever branch are from A, I'll multiply that too. Okay, you can see this is A, so I'll multiply this one with this one. So RAB multiply with RCA. Okay, then division by all this three of all this RBC. If I write for RC, I can write multiply it with the other two branch having node C in common. So what are that two in delta? So RCA and RBC. So I'll write RCA. So with this name, you can just simply see this RC and RBC divided by sum of all the three branches in delta, that is RAB, RBC and RCA. Okay. After this, this is the only two equation that you have to remember. The first is one for star delta. Okay, here RAB is equal to RA plus RB. Again, you can see this A, this B. I will add that 2. Then I will multiply this individual RA into RB divided by RC. And here, if I am finding the resistance RA of star, I will be multiplying RAB RCA and divided by total all three elements of the delta. From this equation, you might have solved this equation. This example, this is a very simple example. Here there is a no star delta conversion. See, it looks like a star, but this is not in star, because I can convert this branch is like this. See, this is a single series branch. If I convert it in series, it will appear like this. I will convert this branch, so it will appear like this. Then these two are parallel, these two are parallel. So I'll have a equivalent over here. So I'm drawing it up bigger. Then these two equivalent are again in series. So I'll draw it a parallel like here. And this parallel can again be formulated like this. Then this one is in series with this one, and then the two are parallel. So this is not a star delta conversion. This is very simple conversion. This is not star delta. This is just series parallel connections. Then see how this is the explanation how that is done. I'm not going into that. Okay, now this one is it's clearly mentioning star delta, but first you have to identify where is your star or delta. So to identify a star or delta, you have to first look into the circuit. which circuit part is not like in series parallel. Like you can see this is in series. Okay, then this part is in series. Okay, if I somehow can say this part is in series, this part is also in series, but here there is cannot consider either this or this. So this resistor is always a questionable, and I am not directly solving a series parallel because this is a delta. You can see this is the first node, a second node, and a third node here. Okay, let me use the eraser. So this 3 point. So this 3 point. This is my first point. This is my second point, and this is my third point. Now you can see there is this resistance, is this resistance, and this resistance. This forms a delta. Okay. Here there is 5 ohm resistor, 15 ohm resistor, and 20 ohm resistor. This forms a delta. Though it's look like a square, but this is actually a triangle because if I draw it like this or like this, that's the same thing. Okay, so this is basically delta, and first I'll solve this delta, then I can convert this example in series parallel example. Okay, so from this what I'll get is this. This is my next circuit. I'll convert this delta to star, and then once I'll convert this, let me show you. See, this is a converted branch. So this was delta earlier. This was delta. Now I have converted that delta into star, and now this star is formatted. Now I can see this is in series, this is in series, this one is in series, this three are in series, and then it will form like this. Once it formed like this, I can see one more delta appearing over here. This is again a delta because I cannot convert this to like series. If I can consider this series, then what about this branch? Okay, so these are not in series. Either not in this series, like it is not like this as well because there is one more branch going over here. If it's series connection, there is no other branch. You can see here, there is no series branch here. There is no element or no wire going through here. Like if one more wire is going through here, I can say this is not in series. So same appears here. Like if I consider this line, then there is one branch going out from here. So I cannot say these two are in series or these two are in series, but this is actually a delta. Again, I'll convert this delta into star, so my star will form like this. There is one more branch and like this. Okay. And let's see a simpler star, that how it will look. If I draw it, redraw it, it will look like this. This would be my first point. This. Okay. I am dismantling this two and I am drawing a new line. So this is point 3. Let us say this is my point 3. Then from point 3 I'll get 2.1. So this branch and my star is like this is my point number 2. So I have dismantled this, this and this. There's 3 branches. Now I can see there is one line going from 1 to B. So this is B. 2 to, so this is 2 to B, and that 2 are connected at B. So this is the simpler network. And if we look at this simpler network, you can see these 2 are in series, these 2 are in series, then this all are in parallel, and then one more series, and you can solve that example. Okay, see this is the same thing redrawn here. So I can easily get the final answer, and you will be having the final answer. Same way, same kind of question can be asked with calculating the current. So first I have to find the R equivalent, and then I can calculate the current. So first I have to go in through a star delta connection. So here there are 2 deltas, and I have to solve that 2 delta. I'll convert that 2 in star, and it will be simple circuit like this. Okay, if you need if you need to see how this game, see this is delta. This is first delta. So I'll be converting this delta in this 3 star element. Same way I will be converting this into star. I am solving two different delta. Okay, so if I draw equivalent, this is my point A, this is my point B. I have dismantled this 1, 2, 3, 2, 4, and 6. So instead of 2, 4, 6, what I will draw is this is my A, this is my B, and this is my C point. Same way, I am dismantling the lower part here. This is my D point and this is my E point. So this is the simpler network. And between B and D, I have one more resistance, so I can draw it like here. This is my B 3.5 ohm resistor. I have to calculate this 3 value. I have to calculate this 3 value from star delta conversion. And then you can see these three are in series with this two be parallel and then finally in the series. So same you can see here. Okay, that star is converted. This three are the star and this three are also star. And then I can solve this problem. Same way, one more example. Okay, I'm not going in detail in this. I'll set the PPT, go through it once, and then let me know if you have any problem. Okay. Okay. Let's not go deeper into this. I'll share this PPT. Just look into that. If you have any trouble, let me know. Now we'll start with mass analysis. But before going into the mass analysis, you must know a basic terms used to define different elements and different loops. So first, there is an element. What is an element? A voltage source or a current source or a passive element like a resistor, an inductor or capacitor can be known as element. Anything that either generates voltage or current or draw voltage or current, like consume voltage or current, is known as element. If it's generating voltage or current, in that case it is known as active element, which does not require any external energy to work. For an example, a voltage source can be a battery. Battery is a voltage source because it does not require any. It will flow a current from that positive to negative terminal, and whatever you have connected, that will be starting. Like if I connect LED will be on, but provided that the battery is pre-charged. Like don't say कि sir battery charge करनी पड़ेगी. Yeah, battery ने obviously charge करनी पड़ेगा, but it is known as active element. It can generate voltage. So there can be a four type of active element. This is a voltage source, a simple voltage source, that is controlled voltage source. Uncontrolled voltage source I can say. Then there is a controlled voltage source. Then there is a current source and controlled current source. That four kind of sources are available, and that four active elements are available. Other than that, there are passive elements: resistors, inductor, and capacitor. Okay. Whenever you say element, either I am talking about a voltage source or a resistor, inductor, or capacitor, or current source. Okay. Then network. What is a network? Something looking like this is always a network. There are multiple connections between active and passive elements in the network. You will see multiple nodes, multiple branches going around. So interconnection of two or more elements can be an electric network. Circuit. If a network contains at least one closed path, it is called an electric circuit. So this can be known as a circuit. A network can be a circuit, but circuit cannot be like a circuit can be a network, but network cannot be circuit. Like if it is open like this, see. See, this can be a network, right? Because the interconnection of two or more elements. So there are two or more elements here. Interconnection is there. Yeah, it is there. So this is a network. But is it a circuit? It is not circuit. Why? Because, sorry, this is not circuit. This is not a circuit. Why? Because the issue over here is it does not have any closed path. There is no closed path. There is a no current that can flow like in closed path loop. there is no closed path. This all terminals are open and single ends. Okay. But here, if I see this, there is a closed path over here. If I put one more resistor over here, it will create a closed path, and then I can say this is a circuit. Okay. Active element, the element which is capable of delivering an average power greater than 0 to some external device or an infinite time interval, an active element. Okay. Can provide power. Being capable only to receive the power is called a passive element. Node. The point at which two or more elements are connected together is called a node. For an example here, this point. Here the two branches are connected. So I can say this is a node. Junction. It is a point where three or more elements are connected together. Okay. See, this point is known as a node. Why? Because, sorry, a junction. Why? Because here you can see a point where three or more elements are connected together. So this is a junction, but this is a node. Okay, this is node. Why? Because here only two elements are there. I cannot say this is junction. I can say this is node. I can say that. I can say this is node, but I cannot say this is junction. Sorry, this is junction. Why? Because there are no three elements. Here there are three elements, so I can say this is a junction. Then a branch, a section of portion of network or circuit which lies between two junction points. Or you can say two node rather, not junctions. Two nodes is called as a branch. Loop. Any closed path in the network is loop. So see, this is a network, and if I say a closed path R1, C4, R2, like A, B, D, a formulation of this is a closed path. So I can say this is a loop. If I consider one more example, a bigger loop like this, then also I can say it's a loop. Again, loop. That means, see, this is also a loop. This is also a loop. But at some point it happens, a loop considers one more loop. So most elementary loop are called as mesh, from which you cannot have a one more loop. An example, if I consider this loop, see my pointer moving over here. Okay. So this path. So if I say this is a loop, but if I go ahead, I can further divide that loop into two more loops, one being this one and the other one being this one. So most elementary loops are known as mesh. So if I consider this, there is no other loop can be formed from this path. So I can say this is my most elementary loop and this can be a mesh. And whenever you perform a mesh analysis, you have to go with this kind of mesh. And that's the next topic. We'll start with the mesh analysis. Uh, just a moment, my that writing pad is switched off, so I have to bring the power cable. I don't have it. So wait for a while, just 2 minutes, and I'll be back. Until that, what you can do is, nah, nothing. Just wait. I'll be back in just a moment. Okay, so let's begin with the mesh analysis. Sorry for the interruption. Okay, so mesh analysis. So today we'll see how to apply mesh analysis, and tomorrow we'll solve the example with a mesh analysis. So first of all, whenever you use mesh analysis, it applies KVL. So if you can say application to KVL is mesh analysis to find out the unknown currents. So it basically use KVL and find out the unknown currents. There would be a one more analysis, that is nodal analysis, where we are going to use KCL. But in mesh analysis, we will use KVL. Where is it as applicable? So it is only applicable to a planar circuit, or you can say a circuit that can be drawn on a plane with no branches crossing each other. So there is two different networks, and if that two are connected in between, in that case I cannot go with a mesh analysis. Okay, so we'll be not having that too difficult questions. So it's like just to uh, basic information, like when it is applicable. So again, this is a definition of mesh. A mesh is a loop that does not contain any other loop. So you have to take elementary loop, you can say. Then the current through a mesh is known as the mesh current, and using that mesh current we are going to find out the actual current. Assume for simplicity that the circuit contains only voltage sources, and if there is any current source, then you have to remove that current source. So you have to assume that there are only voltage sources. Okay, now how to apply this mesh analysis? There are the steps. So first, assign mesh currents. Like where is the circuit here? See, for this circuit, let us say this is the network where I am going to apply my mesh analysis. So first step is I have to find out the loop currents. For an example here, first of all I have to find out the mesh. So let us say this is my first mesh. Okay, there is no other loop inside, so I can say this is mesh 1, and I'll say one mesh is the resistance, that is two different meshes, but we'll take care of that in later stage. Okay, there is one more mesh here. Okay, and there is one more here, but I cannot draw a mesh like this. See, this is wrong. If I draw this is wrong, because I have a one more element over here, and it can subdivide it that loop into two loops. So I cannot take this to combine this big block. I cannot take, but a smaller one I can have. So first of all, I have to decide on which mesh I want to work. So I have declared my mesh. Then what I'll do? Then I'll decide the mesh current. Like what are the currents? Okay. So I'll arbitrarily assume that okay, my first current going through this loop is in this direction, and I will say that I1. Rather writing it, let it be. Okay, so I'll say this is my I1. Then in mesh 2, I'll say my current is I2. Again, I will assume the arbitrary direction. Okay, here it has, they have assumed like this, but if you want to, you can go with anti-directional as well. But to make it simple, always go with single direction. Okay, then I'll say this is my I3 and this is my I4. So assign the mesh current I1, I2, I3, the number of meshes. So whatever number of meshes are there, you have to apply this to each individual mesh. So this is my mesh current I1, I2, I3 and I4. Then in next step, I'll apply KVL to each of the L meshes. So I'll apply KVL on every of the single meshes and use the Ohm's law to express the voltage in terms of the mesh current. So I'll be using Ohm's law to express the voltage in terms of the mesh currents. Okay. So if there is a voltage source, I cannot do that obviously. Like, but for this V1 or V7 or V5, I can do that. Okay. So for V1, I can say my voltage value V1 is actually I1 R1. Okay, value of V7 would be different, V5 would be different. Okay, and then solve the resulting simultaneous equation to find out the mesh current. Once you write down the equation for KVL, you have to solve the equations you get. Okay, how to do that? So first of all, let us see what are the number of meshes available in here. So first of all, let us say what are the number of nodes. So number of nodes here would be this first node, second node, third node, fourth node. Now see, there is no element here, so I can say this is fifth node, this is sixth node, and this is the seventh node. Okay, let me number it for you. This is number 1, this is number 2, number 3, 4. Now there is no connection in between, so this is actually a junction. This line going here, and it is, and this is again the same thing, line coming over here and attaching over here. So this is my 7. So there are total 7 number of nodes. Then what are the number of loops? So we have already identified loop 1, loop 2, 3 and 4. So here I have 4 loops, and I have identified number of branches. Branch kitli hai? Number of branch. Total number of branches available in the network. 10. How 10? Can someone explain? Let us start from here. See, this is my number 1 branch. There is 2 nodes, 1 element, so I can say this is branch, second branch, third branch, fourth branch, fifth branch, sixth branch, eighth branch. 8 are clearly visible. Then this one is the 9th one, and this one is the 10th. 2 voltage sources are also considered as branch. So I have total 10 branches. અહીંયા મેં રજિસ્ટરને નંબર નથી આપ્યા, મતલબ સિમ્પલી રજિસ્ટરને નંબર નહીં આપી દેવાના, because if there is one more element like this, in that case again this would be a same single branch, but there would be 2 different resistors. So હું ખાલી રજિસ્ટરને નંબર નથી આપતો. Keep that in mind. And from this I can easily calculate what would be the number of loops. From this equation b minus n plus 1 is the equation which can get you what will be the number of the loops, elementary loops here. So I'll get 10 minus 7 plus 1, so it would be 4. So I'll get number of loops 4, જે આપણે already અહીંયા calculate કરી લીધી, but actually આ નથી આવે છે આવી રીતે. Okay, now we'll start actual example. So what was the first step? First step is to identify the mesh. So we have identified this is the mesh 1, mesh 2, mesh 3, mesh 4. Sorry, mesh 3 and mesh 4. Then take the arbitrary current. Assume a current flowing in each mesh. Let us say this is I1, I2, I3 and I4. Then the next step was to apply the KVL and write down the equation for individual mesh. Let us do that. Apply a KVL and write the equation. Okay. See, there is a voltage source going in this. Okay, here he has gone in the opposite direction, so he has taken minus Vs2. So here he has taken minus Vs2. Then I am going from positive to negative, but opposite the current direction. See, this is the current direction, and I am going in opposite. So I will say plus V5. Again I am going in this direction, that is opposite to current. So I will say plus V7, and here okay, so there would be a different here because we have 2 different elements over here. Just take the current aside. Current na leso dhyan ma. If we take on the basis of current, it will create an issue. So we are not considering current, but rather we will consider a sign. just take the arbitrary sign of each element. Probably તમને એક્ઝામમાં મેં આ સાઇન આપી દઈશું, like whether this point is positive or this point is positive. I will give you that, and basis on that write equation. So here let us say I'm going in this direction, so I'll write vs2. Now direction change. Let us change the direction. I'm going in this direction, negative to positive, but this is a voltage source, so I'm going negative to positive. That's why I'll get plus vs2. Then I'm going positive to negative, so this sign would be minus, so I will write minus v1. Again positive to negative, so again minus v7. But here if I go in this direction, that is negative to positive, so I'll write plus v5. If you go in opposite direction like this, in that case I will be having minus vs2. Okay, so I'm going actually negative to positive here, so minus vs2. Then I'm going positive to negative, so again minus v5. Then I'm going negative to positive, so I'll say plus v7, and negative to positive, so I'll say plus v1. Okay, see here also negative to positive, and this one also is negative to positive, but this is voltage source, so negative to positive is actually considered as negative. But if it is a voltage drawing element, and in that case if I'm going negative to positive, then I'll consider a positive sign, because this is the voltage consuming element or passive elements. So passive element will change the consumption. So this, either of these two equation is correct. And if you look at detail of this equation, you will see whatever is the negative here will convert in positive, like so. It is the same equation. So I have written the first equation for mesh 1, minus vs2 plus vs1 plus v1 plus v7 minus v5 equal to 0. Then I'll write the currents of this three. So if say v1, what is the value of v1? So I can say there is a current i1, there is resistance ir1, so I can say v is equal to i1 r1. What would be the v7? Anyone can tell me what would be the v7? Value of v7.
I1 R7.
I1 R7. Okay, if you write this I1 R7, you will be wrong. Why? Because if you look at this element is part of two different loops, and at the time here there is a current I1 flowing like this, but I am actually writing the potential V7. So I do not have to consider only this mesh right now, but as an element I have to consider what would be the value voltage appearing across this. So here there is a current I1 going in this direction, current I2 in this direction. So actually my voltage V7 is I1, sorry, I should write it like this, I1 minus, there is current I2 going in the opposite direction, so I'll write I1 minus I2 into R2. Sorry, R7, not R2. Okay, so this is element R7. The current flowing through R7 is actually I1 from this direction, I2 from this opposite direction. So equilibrium current would be I1 minus I2, and the voltage will appear according to that I1 minus I2. So I'll write I1 minus I2 into R7. Same way for V5. See here V5 is in between I1 and I3. So V5 would be I1 minus I3 into R5. So you have to take care of this. Then there is a mesh current, sorry, mesh 2. I will consider mesh 2 and I will write KVL equations for mesh 2. So here my mesh 2 is this mesh. So there is no active element, so I am just writing it like plus V2, then minus V6 and minus, so minus V7. Okay, starting from this point this is plus, so I'll write plus V2 minus V6 minus V7 equation. Same way I'll write the third loop. I'm going from here. So plus V6 minus V4, then sorry, plus V6 plus V4 plus V8 and minus VS1. And same way for this one, plus V3 plus V5 and plus VS1. Sorry, plus VS1. Okay, here I am going in this direction. That's why I have taken minus VS1. Okay. So this is the mesh equations, or you can say a KVL equations of each individual mesh. And then I'll put the mesh currents in here. So minus Vs2. See, I have taken this V1. This is my value of V2 and this is my value of V5. Sorry, this is not V2. This is V7. Okay, V1, V7 and V5. V1, V7 and V5. Earlier we have seen this. V1 is I1, R1. V7 is, there is current I and there is current I2. So I1 minus I2, R7. Same way V5 is I1 going in this direction, I3 in going this other direction. So I1 minus I3 into R5 equal to 0. So this is my first equation. I'll simplify that equation later on. And same way I'll write the equation for the other form. Again, same V2. So V2, where is V2? V2 is here. So single current I2 R2. So I'll write I2 R2. Then again here. So V6, two currents I2 and I4. So I'll write I2 minus I4 into R6. Again 7. So I'll write I2 minus I1 into R. See, I'm consider this. So earlier I have written I1 minus I2 into R7, but here I am writing I2 minus I1 into R7 because I am going in this direction. I am considering I2, and considering I2 I am writing the potential. So I will write I2 minus I1 into R7. Clear? But at that time this two sign will change, like it would become negative positive. So that's why this, see, this is positive. I was thinking that. So I have actually taken minus out, I can say that. This was V2 minus V6 minus V1. So V2 minus V6, see, this is converted to plus. This is also converted to plus because the current was opposite. This depends on positive, negative. We have taken sign, so I'll consider it as I2 minus I1 minus I2, and then I will take minus out. This one is a very big problem. We'll have a small problem first, and then we'll solve this kind of big problems. So these four equations are coming from that. Then from this four equation, I'll simplify this equation on the basis of the current I1, I2, I3. Okay, whatever the resistance, I'll take I1 common from this equation. So I1 R7, I1 R1, and I1 R5. I'll take plus R7 plus 5 into I1. Take this I common in each equation. This is I have taken I1, I2, I4. Here I have taken I1, I3, I2 and I4. And then see, these are the same equations here rewritten, but the Vs2 or Vs1, wherever the source, is on opposite side now. Earlier I have put a 0. See, I have put 0. We'll take Vs2, Vs1 over this side. And then from this, I'll write a matrix. Okay, whatever is with I1, I'll write in this line I2, I3 and I4. So here R1 plus R5, R7, I1. So R1, R5, R7 minus R2 into I7. So I will write minus R7, I2, then minus R5, I3. So I write minus R5 and 0. So basically this is the same equation. See, I1, I2, I3, I4 is written in the other matrix. So if I simplify this, I will be having the same equation. Okay, and then is equal to Vs7, Vs2. So I'll write Vs2 on the opposite side. Same way I'll write for all the. I'll take 8 with I4, so I'll take here. And if I1 is not appearing over here, see I1 and I3, sorry, I1 and I3 are not there. So I'll put simple 0. And now by solving this whole matrix using the Cramer's rule, I can have my answer. Or you can also apply Gauss-Seidel method. But this is equation, so I cannot. But in real example, you will be having the values of R1, R5, R7. So that would be the algebraic value. Like it would be having a real number, and you can process it on Gauss-Seidel or a Cramer's rule. The Cramer's rule is the preferred method. So this is the matrix Ri equal to V, but in the matrix form. What would be the size of R? So size of R is always L by L. What was L? L was the number of masses available in the network. What would be the size of I? 1 by L. Okay. And the vector V is known voltages. We are going with known voltage. Known voltages are the voltages one acting as a voltage sources. These are the some insights, and then you solve this equation, but we'll take that in next class because it's already 10:15. Okay, any question up to here?
No, sir.
Okay, if you do not have any question, you can leave. I'll share this PPT today itself, and if you have any questions, you can raise the question, otherwise you can leave.